Hi, in this video we will prove the existence and uniqueness of second-order linear differential equation. This is done algebraically, so if you don't like that integral analysis, real analysis proof, you might like this algebraic version. It's pretty neat. So let me summarize it here what we have so far. This is the first-order linear operator, and followed by the second-order linear operator. If you carefully unfold this, it behaves just like a quadratic expression of numbers, but there's a slight difference of coefficient of this identity operator I. There's a q prime kicks in. That's the second factor of this operator expression. So if the second-order operator is factored in that form, then you can look at this each of the operator, first order operator, and you can hit it with this 3 operator in this order. Then it kind of annihilates this whole thing. It kind of gets rid of this D. See, this identity shows up. This is good. And this is evaluation operator, so it's pretty easy to calculate this. So you can do this one at a time. So what we're going to do in this video is that we have this product of 2 first-order operators, and by applying this one, we're going to cancel these. This annihilate this part, and that'll give you I of identity operator plus some evaluation operator, and then if you hit it with this part, that's going to annihilate this part. Just like we did this one with an example where Q and R are constants in an earlier video. So here it's just everything written as an operator algebra. The corollary says that if you go through and do the operator algebra carefully, you're left with the following. I is the identity operator, and these are functions. Capital R is the antiderivative of R, and these are evaluation operator, and this is evaluation operator, and these are just integral of a function that is completely determined. So that's the only part that the identity function picks up the unknown function. And this evaluation will be completely determined by initial values. First, just let me show this much of the proof. So this we're applying this operator to this D plus QXI first. So that's why you see this one here. If you pair up with this 3 operator with this whole thing inside, by the corollary I've shown earlier, it's I minus evaluation operator, and I've done it here. And we're going to put these 2 things together and simplify a little bit. All right, that's the next bit. So this one is multiplied to that part I, so it's going to pick up just the whole thing. And this is an evaluation operator, so you can see this whole thing is really evaluation operator. This is going to be a constant function. If you apply a function here, then it's going to be some sort of function, but it's evaluated. So the value of a first derivative and value of the function value multiplied by some known functions. This whole thing is going to be constant function multiplied with EQ. So whatever you do in here, that's going to be completely determined. So that part, D plus Ri, shows up here together with this one, because it's linear, it distributes. Together with this one, it's going to annihilate D and kind of give you a simple form. So that was the result here. And if you pair this up here, and you have identity minus this evaluation function, evaluation operator, and this whole thing is applied to whatever this one is. This is going to be a function that's completely determined under the given initial condition. So that was the result of the corollary. We will use that corollary to prove the following theorem. This is typical second-order differential equation in standard form, but moved over here, so it's more of an operator form. So this is like an operator, second-order operator done to a known function y, linear operator, and right-hand side is the function only in x, and here's some initial conditions. We're claiming that this initial value problem has one and only one solution if this operator factors like this as a first order multiplied by a first order as algebras, operator algebra. Our proof is straightforward. First, uniqueness. Suppose y is a solution, and I did the left-hand side calculation, and after I apply this operator. After you apply this operator left-hand side and right-hand side, this is a result of the corollary that if you have a function also, then this corollary says that this whole operator becomes identity minus this evaluation operator, and this evaluation operator followed by some integral function, integral operator. So if you apply y to there, y is picked up, everything else is completely determined by the initial condition. So what I'm doing here, and I'm applying the same operator to the right hand side, which was the function in x. As you can see, whatever the operator given to a completely given function is going to be a completely given function. So whatever the form is for the shape of the answer is, this is a function with no unknown parts. So if you go through the same operation, it's just pretty much just writing down the meaning of the operator carefully, because there's two integrals involved and I have to use this two different dummy variable to write this iterated integral. Now you look at that massive equation. If you solve for y, you will arrive at it here, and this is what was on the right hand side before, and there's this evaluation part that was on the left hand side and moved over here. You can examine yourself that everything here is completely determined with the given initial condition, and this part here is my RA. It looks like a VA, but this is RA. So y had to be this function. That's the uniqueness. So we prove the uniqueness part here. If there's ever a function that satisfies that second order equation, if it factors, the operator factors, then it has to be this function. That's what this implication means. Uniqueness, under this type of circumstances, we always looked at the reversibility. So this part is a completely determined function, so can we reverse this all the implications so that we can show the original condition, initial value problem is satisfied without actually doing the algebra again. So we will leave that part. It's very straightforward calculation. And if you look at this implication backwards, and they're all reversible. So let me first explain the reversibility from here to the previous level. All I did is moving this massive part to the left-hand side, so that reversibility is simple. This reversibility has to be a little bit careful. Let's look at here. Operator done to the original equation is this 6 operators. First thing done, 3 things done here, and after that 3 things done there. To reverse that, you must be able to find the inverse operator of this one. So how do you inverse that? You will multiply e to the r. That's the inverse operator that gets rid of it. How do you kill that integral operator? Of course, it's a derivative. A derivative done to the left, and it is simply identity. If derivative is inside like this, then it picks up this evaluation operator, so it's not simple. But if you do the derivative later, then it's going to cancel. And multiply e to the negative r again, and e to the q again, differentiate, e to the negative q annihilates everything. So inverse operator of this one is quite easy to see. So if you do that, it's going to kill everything. It becomes this inverse identity operator I, and the same thing is happening here. So you recover this original operator. So that proves that if you start from that massive formula of y, it does satisfy this operator equation.